least that one. Right. Okay. I think we can go. I think it's already recording and we can start the talk.
Okay.
Hey, thanks.
Yes, so please stop here. Have questions, and also my apologies if some of the material is too slow for some of you. I don't know the exact background folks here, so I'd rather go slower than faster. But if one of you just stop me if you think I'm going slow, and then I can skip over some background. Okay. So
Aravind, can I say, so the video only actually managed to capture this board.
which one?
The big one on the left. This big one.
What
That
is
one, I think the video just doesn't reach that one.
Okay, I'm up to here.
Yeah.
Okay. Okay. But this you can see.
Yeah, for sure. Yeah.
Okay, and we go for roughly 2 hours.
Yeah, that's it.
Okay. Yeah. So the local lemma by Erdős is by Erdős and Lovasz, gives some very general, very useful sufficient conditions for simultaneously avoiding a collection of bad events in settings that we see. Okay, so you could ask why in a paper due to its work due to Erdős and Lovasz, it's only called the Lovasz Local Lemma. So the lemma is actually hidden as a small lemma in the 60th 60th birthday celebration volume of Paul Erdős, and in a particular paper of Erdős and Lovasz. But Erdős has said many times that the lemma is due to Lovasz, and he himself used to call it the Lovasz Local Lemma, so the name is stuck, right? But if you can look at this, both in this volume and this paper by Erdős and Lovasz, for those of you with combinatorial interests, it's pretty remarkable. It's a really, and like I said, this is buried as a small lemma in the paper with many interesting results. And Jerome Spencer was the person who could see that this would have many major applications. And since 75, it's become a significant tool in probabilistic combinatorics and theoretical computer science. Okay, so okay, so let's start with an example to illustrate this. So recall case hat. K satisfiability or K CLF satisfiability. We have many Boolean variables. And in process, so think of K as a small constant, if you like, right? Or something, or a slowly growing function of n and n. And process, see what we can see here. Each and all of exactly, let's say exactly K literals, where a literal is either an xi or an xi component. Okay, so these are variables, and literals are these variables union their respective components. Right? So there are a few different definitions for K set, but without loss of generality, for our case, we can assume that for this example, that every clause has length exactly K. Right? So for example, an instance of 3 set could be n equal to 4. Right? This is an example of 3 set. Right? Every clause has length exactly K. And of course, the K set problem is, does there exist a Boolean assignment and assignment with xi's? Also stop me if you can't understand my handwriting, or if my handwriting is small, or if you can move forward in case you can't see my handwriting. Does there exist a Boolean assignment with the xi's such that all Ci gets satisfied? Right? Of course, this is the canonical NP-complete problem. So of course, the problem in general is NP-complete. So we can, of course, expect a characterization of satisfiability, but we can, in the spirit of the phrase sufficient condition, we can ask for some general sufficient conditions for the given formula phi, k sat formula phi to be satisfied. Okay, just a sufficient condition. Right? So here's a simple sufficient condition, simple lemma, right? So let's call this formula phi, KCLF. So let's call it instance phi. An instance has variables and classes, right? So lemma, if k is greater than log n, so here's the simple proof. Again, all of you will probably know this. So assign the truth values randomly. So, or state it a little more carefully. Equally likely, all variables assigned individually. Right? So just a standard random process, just randomly assign true false values to the variables, right? So let
I mean log,
PR,
log, you mean log m maybe?
I'm sorry.
You mean log m?
Oh, right. Thanks. Thank you. We think of m and k m as being approximately the same order of magnitude, but yeah, it should be long. Right? So let ER be a variable in this terminology, be the variable that CR is violated by this assignment. Then the probability that EI happens is in fact exactly equal to the minus k, right? Because the probability that the C1 will get violated is that x1 is true, x2 is false, and x4 is false, which happens with probability 1/8, right? Half cubed. Therefore, the probability that at least one of these is true, right, is less than or equal to by the union bound the sum of the probabilities of the variables. So, okay, we can log in as a simple sufficient condition, right? But here we did not, in going to union bound, you did not make use of any coupling, any kind of correlation between the clauses, right? So remember, the union bound is right if and only if these events are mutually exclusive, right? And that, of course, is never going to happen, right? So this is true on one hand. Okay, so I will bring a lemma to motivate. So notice that, of course, what we want here is the same as the probability that there exists a value. You want to be strictly smaller than 1. Right? So a simple sufficient condition is the union bound. Right? It's called the union bound, or in number theory language, it's called the counting sieve. Right? You're simply adding over the variables that their probabilities, right? The other extreme case, which is also easy, is if the clauses are completely disjoint from each other, right? So the set of variables used in the first clause is x1, x2, and x4, right? But suppose n was quite large, and suppose C2 had x1000, x250, and x400 or whatever, right? Then the set of variables don't overlap at all. The other extreme, not extreme, but the other simple case, independent set. Suppose move to CR, share a variable or letter. Right? Then the probability, again, the random process is the same. Right? So then, of course, we trivially know that it's satisfiable, then tree is satisfiable, but we consider proving it by, of course, we know that this is true, but the proof is do this, let EIs be the same as here, the probability, which is what you want to be non-zero, is now the product of the probabilities of these variables, and all you require is that this is strictly non-zero, therefore the product is non-zero. Yeah? So the other simple sufficient condition is that your variables be independent, right? And it is between these two extremes that the local lemma interprets, right? On the one extreme, you make no assumption about the correlations among the EIs, right? And you just add the probabilities of the EIs. On the other extreme, if you can assume that the EIs are independent of each other, right? Then of course you can come to the same conclusion. Right? As long as no variable has probability 1 over this, right? And you want to interpolate between these two in the sense that suppose every variable in a technical sense that we see is independent of almost all the other. If every EI is independent of almost all the other edges, then you still want something, right? That's the interpolation that the local lemma gives. Okay, right. So on the one hand, there is the counting set, on the other, there is the independent set, right? So okay, so let's try to keep everything here. And yeah, so maybe I'll erase just this part. So yeah, so in terms of the problem that we started out with here, wanting sufficient conditions, we therefore have two simple sufficient conditions that we want to interpolate between. Please again stop me if you have any questions anytime. And again, sometimes people say the writing looks a little small. Let me know if that is the case, or if you want to make any comments, please stop. Yeah, stop. Okay, so therefore, one simple sufficient condition. The entire question is interpolating this. I will write for you what the interpolation is in a minute. Okay. I'll first say intuitively in the sense of each EI being independent of almost all the other edges until we see a simple one simple way of formalizing it. Okay. So I'm going to erase this part out. I'll first start with the simple formulation of the local lemma for the symmetric version, right? And then we go to the more general formulation. There are even more general formulations, and the plan for today and tomorrow is for today to talk about the non-algorithmic, not non-algorithmic, or just the existential versions of the theorems. Existential meaning here, for example, we only say that there exists a satisfying assignment. We don't give a polynomial to an algorithm for it, right? And so, right, so today we'll talk about a number of such applications where we just show that some combinatorial structure exists, right? And tomorrow we'll come up with a polynomial time algorithm to actually extract these structures that are shown to exist by the local lemma. What to me is really amazing is the following, okay, is that the study of the algorithmic aspect has led to more general versions of the local lemma, even that are new, even in the non-constructive world. Right? Suppose you only so for example, people say that Erdős's interests were largely non-constructive. He didn't care about for those of us who are computer scientists, we of course care about the algorithmic and constructive aspect. But Paul Erdős was happy with, generally speaking, with the non-constructive aspect. But yeah, so to me, what is surprising is that over the last maybe 20 years, versions of the local lemma or applications of the local lemma have been developed, which motivated heavily by algorithmic versions of the local lemma that are new, even if you only were interested in non-constructive, non-constructive statements. Okay, so let me say what the local lemma is. Okay, so the LLM symmetry question is the following. Is the simplest, there are even simple versions we can formulate, but this is good enough. We'll define what depends, what we say mean by depends shortly, but suppose for all I, there is a uniform upper bound on the probability of any one of your arguments. Should we turn the light up and will it be clear? Would it be clear the light up?
Yeah, maybe that.
Okay. Please move up if some of my writing is not clear. Certainly stop me if you have any questions. Okay. And so suppose you have these two uniform bounds. Okay. For all of your variables, there is a uniform upper bound P on the probability of the variable happening. There is a uniform upper bound D on the number of other variables that this variable depends on. Okay. Then essentially what the local lemma says up to a small constant factor is that as long as, so of course you would like neither of, it is good for us that neither of these is not, right? The first counting set shows that P being small is good, right? P being less than 1 over n is good. The independent set says that D being 0 is good, right? We want to now generalize both of these. We want to show that, we want to say that as long as P and D are at most reciprocally dependent on each other up to a constant, we are okay, right? Okay, so then, we'll have to say what this is. That's an easy, don't worry about this. It's a very natural definition that we'll see. Then, this is a sufficient condition. This is 2.71. E times, and so, okay, don't worry about the E and the plus one from, okay? Implies what we want. Okay. Okay. So if you don't worry about the E and the plus one for you, okay. But the plus one can be eliminated in many cases. It's needed in some trivial cases, but basically you can forget about the plus one. But the constant E is necessary in general. You cannot improve upon that in general. Okay. So if you don't worry about those for now, you're saying that as long as P and D are at most reciprocally reciprocal in each other up to this constant factor of E, you're okay. Right? Notice that this says nothing about the number of variables n. Right? D can be a constant, D and P and D can be appropriate constants, and n can be very large, etc. Right? In fact, in some applications, the number of variables n is even exponential in the size of the problem space. Okay, so it doesn't. That's why it's called the local limit. You can think of it as a graph, right? You can roughly think of it as a graph where EI, for example, there's a huge number of variables, but E1 is a neighbor of only E3, E10, and E20, for example. You can, and in many cases, you can naturally draw such a graph, as we'll see, right? But essentially, you're saying that there is this very large graph where there are some simple local conditions. The probability of any one node is small enough, and the degree of every node in graph theoretical language, D, is at most some D. And then you have this condition that neither E nor T is too large. Yeah? That's it. Then, regardless of the size of the graph, with positive probability, none of the bad events comes. Okay? This is the, but we will generalize the statement. This is called the symmetric version. It's called symmetric because you have the same uniform bounds for all I. Yeah? You can, for example, make some bad events relatively have relatively higher probability, but have very few neighbors, and conversely have somewhat high probability, somewhat lower probability and very more neighbors. Right? All those are possible. And we will talk about that. Okay. So what do we mean by different solve? Yes. Sorry, one small the 2.7. The base of the natural number. Ah, okay. Not the number of edges, just the constant 2.7. What different solve means is the following. Basically, I'll say in words and then we'll write notes, right? Essentially, it says that, look at this E1. It says that if I condition on anything about stuff that is outside the neighborhood of E1, right? So there are n minus 4 events here, right? There are n minus 4 events here. Condition on anything about them that you want, right? Conditional on that, the probability of E1 does not change. That's what we mean, right? For those of you who have done some associated AI, there are models of dependencies among random variables called graphical models and so. So you may see that in some formulations in AI, right? That's what we want to say, and I'll write that down, right? So in other words, for every EI, there is a neighbor set Ni of cardinality at pose D, such that if you condition anything about the stuff outside Ni, the conditional probability of Pi does not change, right? So basically, this depends on just can be formalized in one way, and I'll give you sufficient condition for this dependence on. This is very, very easy. Okay. So this depends on basically say means the following. For all I, there exists, let's call it a neighbor set. It's a subset of course, 1 through m minus I. Okay. Such that the cardinality of Ni is at most D. That's what this and the probability of Ei given anything about the EJs where J does not lie in I union in I is equal to the unconditional probability of P.
So, am I clear that anything about the EJs is I go over all these events other than I and the neighbors,
And I can
and I can condition on either the event happening or I guess not happening, anything I want.
Actually, that's a good point. In fact, it's something even we don't even need about anything. There's just a specific. Okay, why did I say what it is, right? Technically, this is sufficient, right? In fact, okay, so this is correct, but in fact, we'll see from the proofs that this is sufficient. Okay? In fact, let me say what it is, right? In fact, for all else that is in my non-neighbor set, I union in my component Okay,
Yes.
the probability, the conditional probability of EI given EJ complement is less than or is equal to the probability of EI. This is sufficient. The following suffices. The specific type, the only specific type of conditioning we care about is this. You have EI, and you say that neither this, not that, not that, not that even happen. You will take some number of elements S in the non-neighbor set. Okay? The nodes at distance at least 2 from I, and you say that none of them, some of them did not happen, right? In fact, we'll see, I'll come back to this, even less than or equal to suffices, and that is called the lopsided local lemma. Please tell me if you can't see below the board or come closer if you can. Yeah?
So that's the LLLL.
In fact, that was discovered by Lovasz and Spencer, and that has some interesting consequences. Right? In fact, it suffices. We'll see some nice applications of that. Right? For now, just look at it as this. Okay. Don't worry about the less than or equal to. Right? Look at it like this. Right? And the natural, almost all applications, not all, but everything that we will be concerned with today. Okay, so how do you verify this, right? This looks like a thing to verify, right? In fact, there is a simple, you don't need to worry about it at all, right? Because of the following, right? For instance, look at the satisfied negative problem, right? Intuitively, you will say that, okay, so consider, so let me erase this. Right. So what is this neighbor set? Right? That looks a little bit strange, but let's go back to the set and suppose this clause is extend or x22 complement or x25. Right? Suppose you have this clause and the corresponding variable, again the random experiment is going to be the same. Assign the variables, random. That's it. Right? For now, that's the simple random experiment, the simplest randomized algorithm that we can take off. Right? That's all it is. Right? Then the corresponding variable EI, we can intuitively say what its neighbor set is. Right? Any other clause CJ that contains x10 or x10 complement, or x22 or x22 complement, or x25 or x25 complement. Right? You can say that I depend on those. I certainly am independent. I'm independent of everything that is outside of this.
Yes.
So in a way, this graph is not connected.
It may not be connected. But if it's not connected, remember that then the problem decomposes into its connected components. Right? If, for example, there is no path from this corresponding node EI to E10 to E100, that means that there is one sub-problem and another that can be solved separately. Is that not true? Because there is no way of getting it from. Yeah, that will be useful. Yeah. So now this one we can easily say in general, you can define the neighborhood set. So more generally, the following is a canonical way in which we apply the local lemma, in which this neighbor set could be very, very easy to define. Okay, and let me say what that is. You will immediately see what that is true. A typical, almost all applications. Is called the variable relation. you have some independent.
So can I try to gather my thoughts a bit out loud before you dive in? So okay. So if you have a property which is given by a CNF and you want to know if it holds, that means that every clause holds. Now, what you're saying is that if I take what I think it's what you just said. So if you take a given clause, you look at the variables that are inside of this clause. The only events that you have to worry about are the clauses that share some variable, right? Because if I have a clause that doesn't share any variable with this one, then if it's not satisfied, right? If it is satisfied
And if either it or not satisfied,
or not,
it doesn't.
has no bearing on whether this clause is satisfied or not.
Not just one sense of the clause, any number of such clauses.
Yes, okay, right. So if I take any set of other clauses that don't have a common variable with this one, whether they're satisfied or not is irrelevant to whether this one is satisfied or not if I choose a random assignment. Although in general, the way the theorem is formulated, I mean, there doesn't necessarily have to be some kind of variable structure
Very good.
inside
Excellent.
it,
Excellent. That's
right?
But yeah, there are some applications that are not like that, but almost all satisfy this. Very good. And almost all that we see today satisfy the form.
Okay,
Okay.
yes. Right.
Very good. Very good. Yeah. So not all, not 100%, as you say. Right? So you have some independent random variables. Capital X1, capital X2, capital X1, right? And these are the truth assignments to the variables in our example, right? And each PR is a Boolean function of some subset of these random variables of these HGs, right? You have some underlying independent random variables that drive all your variables, right? And everyone, so in our KCNF context, for example, each EI is a Boolean function of K of these, right? It's some Boolean function. Of course, in our case, it's an OR and so on. But for now, we don't worry about it, right? So we now want to give a simple way of defining these inverse sets, right? And you easily see it, right? Then J non-typic Y is Ni if and only if Si intersects J is non-unique. This is that, right? This is a sufficient way of defining your NRs. Right? So the graph of these ERs is just what is called the intersection graph of the SIs. Right? If you have a family of sets S1 through Sn, each of which, so suppose you have a set system or hypergraph S1 through Sn, where each Si is a subset of 1 through n. Right? The intersection graph of them is precisely this. You connect Ei and Ej if by an edge, if or only if Si intersections. You can easily verify that. Basically, if this is your type of application of the local lemma, then this definition of Ni suffices. Right? Therefore, in applying the local lemma, right, the symmetry question of the local lemma, you just need to see that if this is your setting, you just need to show that each variable has an appropriately small probability, and the number of other EJs that intersect any particular ER in this sense is small enough, is at most. Okay? Then, and you just need to verify that this condition is true. So this is a very easy, you can do this in many, maybe 90% of the applications of the local lemma. The same also in what we call we discuss the general version called the general asymmetric version. There again it will do this, right? But like Bruno pointed out, there are situations where the variables are more abstract, they're not necessarily given by this, where you have to go back and apply, you have to check that this holds, but in fact, it's sufficient that this holds. Okay. Any other questions? Okay. So I keep continuing. So therefore, now that we have stated this particular version of the local lemma, let's see what interpolation we get between the counting set and the independent set.
Yes. Yes, I guess that so the probability that all of the bad events fail so that I have a good case is bigger than 0, but I'm guessing there's a specific bound.
Good. That bound will be exponentially.
It'll be exponentially small.
In fact, we'll see that it's inherently exponentially small. I'll show to you. Okay.
Yes.
So therefore, you don't get a good randomized polynomial term algorithm directly from this.
It'll be really nice to see this example where
It's inherently small.
it's inherently small. Yeah.
I'll in fact give you 2 proofs. One is easier, and the other will show you an interesting tool that can be very useful for. It's a theorem that is less known. I'll show that also. I'll show you an easier proof and a slightly more involved proof that uses an interesting tool. Both of which show that this positive probability in all cases of interest is essentially very, very small. Okay, very good. Okay, so we'll do that. But yes, so but before that, okay, why don't we? Yeah, please to ask questions like this. It'd be interesting to sort of deviate a little bit from, I don't have, very, extremely specific plans. So, happy to. Okay, therefore, corollary. Here's P with P laws overlapping in the sense that we've seen. At most so there is a corollary for case. Because the probability P is 2 to the minus k, right? So even if k is a small constant, say 5 or 10 or something, you get some really interesting, completely unexpected results. By the way, you can ask if this is the best. So now you can ask, is this, now forget the minus 1. You can ask, is this the best possible constant? 1 over e, right? Notice that I could have done a little bit better, right? For example, suppose the crosses intersect heavily, but for example, but notice that roughly speaking, if I'm class Ci and I contain the variable x5, right? I'm happy about other classes that also contain x5. My problem is that those that contain x5 complementary. Right? Because if they are true, I'm probably hurt and vice versa, right? Therefore, and on the other hand, for variable xi, if it heavily dominates the formula as compared to xi complement, then it's perhaps you're probably in good shape if you make xi equal to 2, right? Because if xi appears in suppose it xi appears in some way in 1,000 of your classes, and if in 990 of them it appears as xi, and in the remaining 10 it appears as xi complement, you're probably well off, with high probability setting xi to true, right? Therefore, one can roughly imagine that The worst cases are when the formula phi is balanced, so to speak, when every xi appears roughly the same both ways, right? That will help you save a factor of 2, roughly, right? When k is asymptotic, think of k as your asymptotic parameter, right? Then forgetting these additive constants and so on, right? To within lower order terms, you can even get a factor of 2, overlapping at most, you can get a factor of 2 in the numerator. Okay. Up to 2 to the k times 2 over e. Plus some lower order terms, you cannot avoid those. As long as that is true, you can still do it, right? But we are not getting into that. That's more the province of the lopsided local lemma, and it needs more work. Okay, so right now we won't talk about that. But in general, in terms of existentially optimal results, you can push this a little more. The constant 1 over e can asymptotically become, as k becomes large, can become something like 2 over e. Okay, but of course there are these lower order terms that vanish as a function of k. Okay, but we won't go into those. But already you see that even for small k, say k equal to 10, right? You see that, for example, if every clause intersects at most 300 other clauses or something, then the formula is satisfiable. There seems to be no other way to prove such a thing, right? In fact, one of the striking properties of the local lemma is that, yeah, it was published in 1975. Joel Spencer, I think, published the first other major application around 1977. And for the next several decades, there were many such applications of the local lemma. For every one of them, the only known proof is through the local lemma. Right? It's a simple lemma with extremely powerful applications. Right? And you'll see that even the proof of the lemma is very short. It's an appropriate careful induction, that's it. Okay, so not very long. I'll give you the intuition behind it and then we'll be good. But yeah, you get this correct. Right? Now let's address Bruno's question that just why this probability is inherently small. Okay, so why we cannot hope that if you just simulate this process, then with reasonable probability you'll avoid all the problems. Okay? So again, the regime that we are interested in.
Aravind, can I ask you, so what's your plan for the rest, whatever time we have?
Very flexible. So today if you tell me that certain topics are of interest, we can do those. There's a whole range of stuff. Okay, but the higher level plan is to cover many non-constructive aspects of the local lemma today. And the more constructive, there was a breakthrough by Moser-Tardos in 2009 and 2010, which I mainly want to cover, and other such things to watch. But yeah, basically, yeah, right?
So I guess speaking from a very selfish point of view, so I would love to see a proof because it's been very long. And if you say of the lemma, so whatever simplest proof of the simplest, so I'd like to do that. I would also like to see what kind of properties can you express like with these kind of local.
Good.
Right, so
yeah.
Right, so examples actually. So especially if there's some kind of pattern that. Like you look at a property and you think, oh, this is maybe a local property, or maybe it's not, or
Sure.
things
Let's
like this.
see a few applications. Yeah. Why don't we do all that for today? Yeah, we'll see several applications. Okay, let's do the following. I showed you a proof of the lemma, but even before that, I showed you that this probability really is inherently small. I'll show you a proof of the lemma. I'll show you more applications. I'll give the more general asymmetric version of the local lemma. We may quickly mention some proofs of some applications of that and stop today and we'll continue to move. But the other thing is, and what I'm happy to do is, first of all, this is my first visit to Portugal, and thank you again. I mean, it is Bruno's work that actually attracted me here. I read about his work, and then there's all this beautiful stuff on catalytic computation and so on. Right? So very happy to be here. What I cannot complete tomorrow, I'm happy to not write detailed notes. I didn't have time for that, but I can write some points about some of the important points that I would have liked to cover, but don't have time for it. Sent to you, and you folks can investigate that for me.
That'd be wonderful.
By the way, may I know? So, of course, I know Tulasi, Bruno introduced. Can I know who the three of you are?
I'm Francesca, and I'm starting my PhD just now. So,
in computer science or math?
math.
Yes. In what area?
She's my PhD student.
Okay.
Not that, yes, with the.
Okay.
Yeah. just out of curiosity, because I'm on job.
You're a doctor. By researcher, you mean you're a postdoc?
Sorry,
Are you a postdoc? You said you're a researcher?
the researcher, yes.
Meaning you're a postdoctoral researcher or?
Well, I will start soon a position as professor.
Oh, I see.
But I was researching.
Okay.
Yeah, I'm a professor here. I come more from the theory combinatory strategy of.
Oh, there are a whole ton of applications in combinatorics. Some of them in number theory and combinatorial number theory as well. I'm just trying to see if I can think of a quick number theoretic proof. Sorry, number theoretic application. Sorry, I'm blanking out a little. But why did I give you some excellent references right away? So that even if, so for more reading of the local lemma, right? The Lovasz Spencer book is definitely an excellent, okay, so references. In fact, for those of you interested, since many of you are interested in combinatorics and computer science, references. One is the Lovasz Spencer book, which gives a ton of applications of the local lemma. Let me also point out my student's thesis. One of my students, his wife is from Lisbon. So, he wrote an excellent PhD thesis. I was delighted to have him as a student. This PhD thesis from 2015 is excellent because it goes way beyond. And if any of you want, I can connect you with him. He has continued to work on the local lemma as well as many other aspects, and he certainly knows all the modern stuff, most recent stuff about the local lemma far better than I do. So I would, these three are, and the original paper is a pleasure to read just for the set of combinatorial ideas that they put out. The Lovasz Spencer book has both the lemma, its applications, the algorithmic version, and so on. Also check out David's thesis because he goes way beyond a lot of these things. Okay.
May I ask, what was the original goal of the original paper?
The original paper was on an application called hypergraph 2 coloring, which is similar to satisfiability, right? So it's okay, good. So in satisfiability, you have two choices for every variable, and a clause can be violated an OR clause can get violated in only one sense, right? Right? There is precisely one assignment to its k variables that will violate it. Right? In hypergraph 2 coloring, you have a hypergraph. A hypergraph is just a set system. It's a family of subsets of a set, right? And you want to color, again, you have two choices for each variable, for each vertex or variable, red or blue. And what we want is that no set is either all red or all blue. Until they came up with some sufficient conditions. For again, and hypergraph 2 colorability is again an NP-complete problem. And they came up with some sufficient conditions. And my collaborator Jaykumar Radhakrishnan and I, we improved upon some of those. But yeah, that was the original. So the original paper is a lot about hypergraph problems, especially hypergraph coloring problems. So it's a really great paper. Okay. So what we see an easy proof that this is inherently very, very small, although non-zero. Okay. I'll give you two proofs. Like I said, the second proof will show you one useful tool that may help you in your research. Keep this in mind. This is the most common type of application. So the notion of dependency is very easy to characterize. Okay. So notice that, I mean, so the real power of the local lemma is when this 1 over p and d and so on are either small constants or logarithmic or polylogarithmic or something like that in n. Okay, the number of variables is n, right? Right? And 1 over p, d, and so on are much smaller than n. Okay, so that's the you can even do okay, so take the square root of or whatever, right? Up to, but not extremely close to it, right? So let's see one, right? It's very easy. You have this graph, right? This dependency graph between the AIs, right? Right? So remember the dependency graph. Right? Remember that if your degree max degree is small, then there is a large independent set. Right? Therefore, there exists an independent set, a set of vertices with no edges among each other within each other at all, of size at least m over d plus 1. This is an easy exercise for you to do. In a graph with maximum degree d, right? So there exists such an independent set, right? Therefore, the probability that you want, which is this, notice that it's greater than this probability, greater than or equal to this, of course, because here you're really asking about the subset of the events, right? But now these are independent. Therefore, this is greater than or equal to 1 minus p to the power of the cardinality of s, which is basically assuming that p is not terribly close to 1, which is
Sorry, you mean at
reasonable.
most?
This
Sorry,
is like sorry,
you mean at most, no? Or am I wrong?
at least.
The
EI,
probability,
EI complement.
the
Because
probability.
EI is at most p, so EI complement is at least 1 minus.
No, sure. Oh, no, wait. So the probability that all bad events, all good events hold. Oh yeah, it's at least a probability, of course, in some.
Sorry.
No, I'm sorry. It's at most.
Sorry. Yeah. So this is at most. Sorry.
Probability that all good events hold is at most the probability that the good events in S hold, yes, and that.
And that can be equal to that because maybe it could be that these are all equal to that. So this is possible. This is possible.
So for some specific choices of EIs of this kind of scenario, it's possible that this is actually 1 minus p to the power s. Yes.
So it's basically like e to the minus m over d squared. Okay? M over d squared. Right? And we think of d as much smaller than m. Say d is like at most m to the 1/3 or something, then this is exponentially small. In fact, the cases of interest that we saw had d being a constant, right? Like k sat and so on, right? With k being a constant. So this is truly inherently small. So this is proof 1. Let me give you another proof. Let me show you a proof that I think is somewhat less known. Okay, there is a constant C in the exponent and so on, but I'm not worrying about those. There is a constant C. But essentially, conceptually, it's exponentially small in m over d squared, which is really very, very small because we, for example, take d to be at most m to the 1/3 or something.
Sorry, where does the C come from?
Some constant because P is like 1 over d.
Ah, yes, I see.
So it's a
So there's some.
So, okay, so let me write this properly. So therefore, the probability that the local lemma guarantees the positive probability is unfortunately indirectly small, right? It's not like 1 over polynomial in M or something. Okay, in the regime solutions.
Okay.
Let me show you another proof, right? And that proof heavily is built for this kind of application. This proof did not assume any such model for the application of the local lemma. Now we are going to assume this model, and then I'll show you a different proof using
I guess a concrete example would be this K set, right?
is
Because then P is exactly 1 over 2 to the K.
and d is like 2 to the k. So
Right.
proof 2.
It's proof 2 that the gap is inherently small. Or what?
Sorry?
Proof 2 of what? Sorry.
This is proof 1.
Of this claim that the gap is.
It's a nice theorem. The last author gives the same last name as me, but it's not me, so I'll write his full name, Srinivasan. So let me state what the theorem of GLS says this. It's a very useful theorem, that's why I thought I'll show you this. This theorem, I think, is relatively less known. GLSS is about the following. So suppose you have this model. You have these independent. Okay. And then some Boolean functions of these. So for example, EI is a Boolean function of x1, x2, and x20. So construct this bipartite graph. Construct this bipartite graph where so again, what is the setup? You have independently x1 to xn from any sets, right? It doesn't matter what the support of each xj is, it's some arbitrary random variables, right? And then Boolean functions. So I'm telling you the theorem of GLSS. It's a very interesting, useful theorem.
I'm sorry, but what is independent here? Because,
These random variables are all independent.
okay,
Suppose you have a collection of events. What you're really interested in are these events, okay, even through E, right?
okay,
But they're driven by these underlying independent random variables,
okay,
where EI is a Boolean function of some subset Si of 1 through n. For example, in this picture, Si is just 1, 2, 20. Okay.
okay.
You can draw this bipartite graph, right? Then the dependency graph that we were interested in here in the local lemma is the dependency graph on the EMs, where, for example, you would put an H between E1 and E2 if and only if they share a variable. Right? That is the dependency graph that we were interested in. Right? And so, just as a useful case, right? Suppose the maximum degree of any vertex on the left is k, and the maximum degree of any vertex on the right is k prime, right? Then notice that with the dependency graph among the EIs would have maximum degree at most k times k prime. Okay? Because you reason that if you look at EI, you would say I am dependent on at most k prime variables. Each of those variables influences at most k xj's. So my total number of neighbors is at most k times k. You can save a little bit of that, but basically it's the product of k and k. So the dependency graph among these can have large degree, but sorry, I shouldn't use k. Let me use L and L prime, right? So, but the theorem of the theorem of GLSS has nothing to do with the local lemma, right? But I'm going to apply it in the context of the local lemma if our local lemma application is of this type, which, like I said, is a vast majority of the applications of the local lemma, right? Right. Now, the GLSS theorem says the following. So, I assume all of you know the Chernoff bounds, right? Chernoff bounds are about the deviation of sum of independent random variables from which mean, right? So, then GLSS show now, suppose, okay, so now what random variable are we interested in? We are interested in the number of these that happen. Right? In the context of the local lemma, you want the number of these that happen to be 0. Right? But suppose you're interested in that number in general. Right? For example, the motivating case, the motivating notation for us is that each of these has probability P of 1. Right? So the expected number of them is m times P, but they're not independent of each other. Right? But you can ask about, so consider the random variable y that counts the number of the bad events that happens, right? And assume that, for example, each is probability p. That doesn't matter too much, but then you can ask what is the probability that y is greater than 2 times mp, right? Which is the probability that it goes well above its mean. Or what is the probability that y is at most 0.6 times mp and so on, right? And the Chernoff bounds give you good bounds for that, right? Right. What GLS is saying is that for either of these scenarios where you're interested in y going either above its mean or below its mean, if you want the bound of the probability and upper bound of the probability, you can first pretend that these are independent and take the Chernoff bound that comes, right? And take them to the power of 1 over L, where L is the maximum left degree. In other words, the theorem said requires nothing about the maximum right degree. For example, the right degree could even be, equal to n. That's okay. But what the theorem says is that all that matters is really what is only the left degree. Right? So you can think of it as, so suppose left degree alone the maximum degree of any vertex on the left is L. Okay. So in their paper, they call it K, but of course they're using K for K sat and so on. Right? They call this a read L family. Right? It's a read L family because every variable on the left is read almost L times in constructing the variables on the right. Right? Then GNSS say, so then GNSS so this convert every EI from true false to 0 1. Right? So this random variable is just one if EI appears and 0 otherwise. So chi of EI is just the indicator random variable for the given TI. So you count one for every EI that happens, right? So it just counts the number of bad events that happens. And the GNSS error
Oh,
children of referring.
seriously. So let me try and understand where you're going with this. So so you're saying that it's not only is it exponentially unlikely that they all the bad events fail, it's actually going to be exponentially unlikely that the number of bad events deviates from the mean.
Exactly. Very. That's it. Similarly, that's the second part of it, right? Same thing. So what we mean by this is, in order to calculate this, pretend first that these are independent, right? And get the corresponding churn of 1 and just raise it to the power of 1 over. Okay. In particular, yeah, the probability that y is 0, let's just look at that. The probability that y is 0, if they were all independent, this probability would be at most e to the minus np. Now, you get a 1 over L furthermore in the exponent. You can easily verify the probability, they're all independent, and each EI complement is probability 1 minus p, and all of them should happen. That is 1 minus p to the power of L, which is less than or equal to e to the minus np. Right? And you just naively apply the e to the minus np and then take a 1 over L. That's it. Okay. You get, so this is the general GNSS theorem. This is the general theorem. I find it surprising. It uses information theoretic ideas, although we have a recent paper where we give, it's a really nice paper, a very powerful result. I still don't get the full intuition behind the approach to the paper. It's a relatively short proof, but they say, they use what is called Scherer's lemma for the pullback Hilbert divergence. They develop a Scherer's lemma. Somehow, I still haven't kind of grokked it, so to speak. So we have, a separate proof from this year, which maybe, to me was a little more complex. Okay. So anyway, you have this. Therefore, therefore, we see that, for example, in our local lemma context, you will get the probability that you avoid all the variables, which is this, is less than or equal to MP over L, right? And that is less than or equal to this, then the local lemma proof of given. You get an even smaller performance probability, right? Because what is the capital D? The capital D is the dependency, max dependency among these. Right?
Like L
That's a key step for sure. In fact, it will be something like it could be something like L times L prime, where L prime is the maximum value. But you completely avoid L prime, which was implicitly present here. So you can do slightly better. Right? I want to show you this also. This seems less known, right? And this GNSS table will be of use to you because many random processes that we are interested in, this E1 through EM, are actually driven by some underlying independent variable. So if you can understand something about them, you can, the large deviations of the number of these one can control some. Okay, so essentially I've given you two proofs to show that, unfortunately, the probability, the positive probability that we are interested in is typically inherently very good. So in particular, if you just run this random process, for example, for KSAT, the probability that we get what we want is very small. So you really want, once you are interested in an algorithmic question, which we'll see in the next class, you really need some new ideas. Okay. So now let's give a proof of the local lemma. Right? There is some, So I'll first show you a reconversion. And then you can build on it a little bit to get this started. In other words, instead of the constant E, I'll show you a proof with a constant 4. It won't require the +1, right? And then there is some simple intuition. Any questions about this? Okay, so let me erase these. Keep this in mind.
Wait, are you going to prove it in the variable version or just in general?
In general.
In gen-
Hello, can you hear me?
Yeah, Suhil, you have a
All right.
question.
I was just wondering if there's a variant of the Lovasz Local Lemma where, so in this case, we're saying that every event is independent from all of its non-neighbors.
Yeah.
Is there a version in which you don't require full independence, but just like mutual information is small or something?
Very good. What? Okay, that's great. I'm sorry, I wrote there and I realized
I moved the
you
comment.
moved it. Okay, great. Okay.
Mhm.
Good. You can ask. Excellent question. Okay. One can ask. Okay, so please tell me if your question is correct. If I understood your question correctly, you're saying what if with the non-neighbors? Sorry, are you okay? What if with the non-neighbors, maybe the total mutual information pairwise between EI and all the non-neighbors is small enough, right? Is that what you're saying?
Yes,
Okay.
exactly.
Okay, so what if, excellent question. What about other notions of non-dependence? Let me not say dependence, but non-dependence. For instance, for all I, the sum over all j on the outside the neighborhood set.
Maybe you just
Oh.
want, maybe you just want like the mutual information between xi and
Everybody else.
everybody else, right? Because that will include all. It's not just like the pairs.
Okay, so
So it's like the information between xi and the concatenation of all xj for j not in n, something like this.
okay. What is the
Yeah,
inverse I for the
I, yeah,
information?
so you'd write like I of xi and then whatever. Yeah, that sequence here.
and here xi is like the indicator random variable of ei, right?
Yeah, xi is the indicator variable. Oh, xi is not
Yeah,
the,
yeah.
sorry, xi is, and it's not the variables, it's just, yeah.
With this one.
Yeah.
Yeah, suppose that.
I don't know the answer to this, but let me answer a closely corrected question. Okay? Or right?
Well,
Right? What if you ask this, for example?
that can only be bigger than the first one, so I think, right?
Uh,
Oh, no,
Right.
it
So that's a
cannot.
stronger
No,
statement.
it cannot.
You're only taking one pair.
Yeah, pairwise, all right, yes.
Right?
Oh, right. So it could actually, yeah.
So you would ask this, right?
Right.
Maybe.
Yeah.
At least let me show you that this formulation may not lead to may not always lead to something interesting, because the EIs could be pairwise independent.
Right.
In which case,
Right.
these are all zero. You can come up with situations where with pairwise independent random variables, where therefore this is zero, but still some global conditions are not true with positive probability.
Right. Right.
Okay, but you and Bruno's first question, which is this, in general, I believe that these are less explored. I don't want to say, so this, I don't know what the, I have wondered about these, and I think this formulation is nice. But to my knowledge, not much is known. So for instance, take this person, what can you say? I mean, there's all kinds of cool results in combinatorics about long range dependence and so on. I think one can say something. You see, for example, the work of Jeff Kahn from even the 1990s. Okay, so please check these. Again, I don't know the state of the art, but notions of long range dependence, some form of decoupling. For example, you have some random process on the graph, and what you want to say is that what happens to one vertex is largely independent of what happens to vertices that are sufficiently far away. Maybe C log n away from it, the graph, right? So words of I don't know if they use the same terminology, but words of Jeff Kahn. There was even in the 1990s, in some of his breakthrough papers, again, I only know Prasad Tetali and others. But there may be something there, but in general, I think not much is. Okay. Does that partially answer your question?
Sure. Yeah. Yes.
Yeah. So check out these works. So now let's try to give a proof of the local lemma symmetric version. So I'll first show you a slightly bigger version using 4, and maybe give you a simple exercise to strengthen your sort of your familiarity with this to make the constant E. Okay? So, okay, proof. So this is so you want this is what we need to show, right? Okay, so let me
Maybe
less than
EI bar, I guess.
yeah, or let's do it this way, okay? This is necessary and sufficient, right?
Right. That wasn't that our assumption, more or less.
Sorry.
Our assumption was that this was basically equal to PR of the I. Did I get that right? Or
So here,
I mean,
no, the solve J less than or equal to I minus one. I may have many neighbors.
of course, yeah. Before it, yes, of
Yeah.
course, please.
They're just indexed smaller time, right? Okay. So suppose now here is a wrong proof, but we'll fix it. Okay? So you have so there is suppose this is the name of this. So this is suppose look at the neighbors. So let's say AI is this. Okay. AI is the set of nodes here that I depends on in our context, in our sense, and there's a complement here. And VI is those that it doesn't depend. Okay. So for example, let's say I is 7, AI is let's say 2, 3, 2, 3, 6, and the other is okay. So for example, so what we're saying is, if you look at the indices 1 through 7, right? In this conditioning, we are interested in this condition. We want to show this. Then, in fact, EI is independent of these, right? It only depends on 2, 3, 6.
Mhm.
Right? So then here's the wrong proof. Suppose we've written, so this is what we have. This is wrong, but let's try this out, but we'll fix this intuition, okay? But the intuition is correct. Suppose we say wrongly that we only care about those in AI, J in A of I, of Z complement. Okay, we're saying that, you know what, I am in E8, right? I'm looking at everybody. I'm conditioning on E1 complement, E2 complement, up to E7 complement here, right? I'm saying that I'm independent of among 1 through 7, I'm E8, I'm independent of 1, 4, 5, 7. So why do I care about those? I only care about these. I'm independent of the other stuff. Of course, this is wrong, right? But suppose we continue with this. Well, if this was correct, right, then we'll be done. Why? Because remember. So the useful thing to remember is this, right? So suppose we assume that 4PD is less than or equal to 1, right? Then the number of terms here is at most d, right? The cardinality of AR is at most d, right? Yeah, so yeah.
So
Here's the
my
point.
assumption is this is just the probability of EI, right?
Sorry.
Isn't our assumption that this?
Sorry. No. These are the ones I'm dependent on.
Oh, sorry, yes,
Dependent.
okay, yeah, my bad,
So,
again,
so I say, you know what?
Yeah.
The stuff here that I don't directly depend on, I can just throw away. I don't depend on those, so I just throw away. I only retain those that I depend on.
that are the dependent,
Right?
yes,
So, right, of course, this is a wrong lead, but we'll fix that, right?
okay.
But this is going in generally the right direction, right? So, okay, so let me erase this. So the intuition is the form. Intuition is the form. Okay, so we complete this wrong proof in a minute. But the intuition is, if you have a conditional probability, if the probability of B is bounded away from 0, so remember, if what you're conditioning on, so I should use A and B, let's say U and V, or Y and Z, is generally okay if, remember that if you're conditioning on something with probability too close to 0, all kinds of crazy stuff can happen, right? This conditional probability can be very different from the unconditional probability. But if the probability of what you're conditioning on is not too small, we can do something, right? So in this case, we only want an upper bound of this probability. You want an upper bound that is strictly smaller than 1. But let's look at both lower and upper bounds, right? First of all, upper bound is even easier. The probability of y given z is the probability of y and z divided by the probability of z, which is less than or equal to the probability of y divided by the probability of z. This is in fact what we use, right? And as long as the denominator is not too small, you're hopefully, right? And let's also do the lower bound, although we don't need that here. So I'll go a little bit faster. The numerator I'll write as the probability of y minus the probability of y and z complement. Right? So z complement. Right? And the probability of this whole thing is less than or equal to the probability of z complement. Right? The probability of y and z complement is less than or equal to the probability of z complement, and there is a negative sign here. Therefore, this is greater than or equal to the probability. Although this is not always useful, you can still at least consider this. And if the probability of z is now large, right? Then hopefully this is close to 0, this is close to 1, you're still maybe okay, right? This is a little more dicey because it depends on, you're subtracting two things, but at least, conceptually you're probably okay. But anyway, we mainly need the first one, right? So I even erase this. We don't even need this one. So we don't even need this one. Okay, so therefore, this stuff we can continue. So suppose we have made this wrongly, then we just use this. Okay? We just use this. Right? This is less than or equal to the probability of P9. And we hope that the probability of what you're conditioning on is not too small, and that is indeed true here. So I will again write this. I write the denominator in complemented form. This is just ER, not EI complement, EJ, not EJ complement, right? Because I've just written the complement. I've written the same probability letters, right? And this is okay, because remember, you can now apply a union bound to this. Each of these is probability at most P, and there are only D terms here, and P times D is less than or equal to 1/4, right? The point is, you can apply a union bound if the number of terms the union bound is not too large, right? Therefore, this is less than or equal to, assuming, and here of course we can even assume this is not EI complement here, y1 minus pt, right? Which is indeed less than, that's the other thing. Right? This was a wrong proof, right? But it gave us some good idea. Essentially, we could not go from here to there. We just have to be a little more careful. But if we get something like this, then we are in good shape. Right? Now, okay, sorry. Now I'll assume this and give you a rigorous. Okay. What we have to do is we just have to do this by induction on the number of terms here, right? But get a good induction hypothesis. Okay? So keep this wrong proof in mind. I'm going to erase the wrong proof. Okay, but we use some of the ideas from here. But the conceptual picture is this, right? That don't worry about the second part now. Right? The first part, it is just this. The probability of y given z is always less than or equal to the probability of y divided by the probability of z. It is useful when this y is an undesirable event and z happens with relatively high probability at least. Right? Then you can show a good up and down on the conditional probability of the undesirable event y. Okay. So let me, so I'll erase this, but keep this intuition in mind. Okay, so this is what you want to show. So now again, I'll assume that I'll make a slightly stronger assumption, not just EPD, but 4PD is less than or equal to 1. Okay, and remember, this is what you want to prove. In order to do that, we're going to show a more general statement and prove that by an appropriate induction. Okay, so first, okay, so remember there is one trivial case when this is true, but there is not true, which is if P is equal to 1, but D equal to 0. Right? If P equal to 1 and D equal to 0, then the bad events are independent of each other, but they may happen with probability of 1. Right? In that case, also you can't say anything. So let's say D equal to before, in other words, therefore P has to be less than or equal to 1. Okay? So D, we assume, of course, that D is greater than or equal to 1. That's the only interesting case. Therefore, in particular, P is less than or equal to 1. Okay. Now, in order to prove this, let's prove something stronger by induction on what? Induction on what you'll see. Okay. So now show. So remember, this is what we want to show, right? For all of them. Therefore, show. For all one. But now also expand the set of indices you conditions. For all this that does not contain R, let's now show by induction on the cardinality of this And we don't just want, I mean, this is too weak, right? You need a more concrete bound. I'm going to show this is less than or equal to, for example, 2. Of course, where did I get 2t from? Of course, you mess with the constants and you see that 2 is the right thing. And this is what they showed the original thing. Okay? And P is less than or equal to 1/4 because of this, so this is the valid probability of the bound. Right? This is what we're going to show by induction on the size of S. Okay, so in other words, we will read, let's interchange the quantifiers. For all S, you want to show the following. For all I not in this, we'll show this statement by induction on the cardinality of this. Okay, this statement we show for all not in this. Okay. So the case 1, of course, if S is empty, implies right? If you're conditioning on nothing, right, then what you have here is that's one base case. The other easy case is if nobody here in S is a neighbor of I. Right? If in the dependency graph, if everybody here is a non-neighbor of I, right, then of course by independence, in base case 2, this is an I is equal to empty. Because again, okay, okay, we want to show this, right? So again, you'll split this J into 2 parts, AI and AJ, and AI and BI and fit. Okay. So fix S, fix I, okay, fix S, and then
Okay.
take any I with, this is the only interesting case.
Okay, we can even assume that the new element is a neighbor.
I'm sorry?
We can even assume that the new element in S prime, I guess, or S is a neighbor of I, right? Otherwise,
No, assume, this is an induction hypothesis on all S, right?
right. But let's
So-
suppose that S has K neighbors of I. We just keep removing neighbors of I until we get none, and then we use base case 2, right? So
We can.
we can assume that the difference between, am I wrong, or are we going to use?
Why don't we see what the induction is? So yes, so again, we're going to split this set S into one part that PI depends on and another that PI doesn't depend on. like what we are interested in, which is this term. So now let's pause and try to parse the statement, right? So EI is independent of this stuff. Right? EI is independent of this stuff, which we somehow want to make use of, right? Good, very good. What we know is that the cardinality of A is small, is at most D, right? Cardinality of A is small. The cardinality of B is maybe very large, but thankfully EI is independent of everybody, right? Is EI is independent of this stuff, right? And of course, remember, because of this, S intersect Ni, this part is non-empty. We're going to apply, we're going to apply induction. This is S intersect Ni is not empty. Just a minute. So you notice that the cardinality of B is strictly less than the cardinality of S, and we're going to use the induction hypothesis. So let's say, let's for simplicity, suppose we write is, let's say, is equal to, by rewriting the indices, let's say equal to 1 to E. Let's renumber the variables. First, for simplicity, and B is this. Right? So in particular, T is positive. T is at least 1. Right? I'm just renumbering or reindexing everything so that A is just 1 through T. Okay. Okay, good. Now, let's think about this. Okay. So let's call this event U. Let's call this event V. Let's call this event maybe not independent and independent of some. Okay. Okay. So you see, notice that you have here is guiding. Okay? So the probability of EI given not independent and independent is the following, right? By Bayes' theorem, this is equal to the probability Bayes' theorem. This is the probability of EI and NI given I divided by the probability of NI given I, just by Bayes' theorem. Okay. In the numerator, we're going to apply induction of the denominator. For the numerator, we're just going to say, just bear with me, it's not difficult. So the numerator is going to be just the probability of EI given I divided by the same denominator. But then EI is independent of 1, right? EI is independent of everybody here. So the numerator you just get this. That's when they're equal to the P divided by this denominator, right? Okay. So this stuff, right? We have rewritten this later, and we want to show that it's at most 2P. Right? We have now shown that it is at most P over the denominator. Therefore, we need to show that the denominator is at least a half. Right? We want to show that the denominator is at least a half. Right? And that's not too difficult.
Now using induction, I guess. Or something.
You use induction. That's it. So, okay, so this stuff, the denominator. Now let me erase the top. So can we erase it?
Because D is at most 1/4P.
Exactly.
We do a union model again.
Exactly. And yeah, we use union one, exactly. So what the probability of Ni given I to be greater than or equal to half. That is the probability of Ni complement. Ej given is less than or equal to half. Right? I'm just looking at the complementary equation, right? This stuff by induction is then is like this supposed there are d terms. Just apply the union bond. Induction plus union bond. Gives you that this is less than or equal to 2PD. Right? There are d terms here, each of which is opposed to p, right? So let me write it as 2p multiplied by d, which is less than or equal to half, which is what you have to show. But all of the intuition is really, most of it is buried in the wrong proof that we show. Okay? That's the, essentially you're saying, as long as, you see, the point here is this, okay? In the numerator, this probability of I is actually very small. Okay? The probability of I is very small. So you can't naively, do the stuff that we applied there. But here you use the fact that you can knock off this Ni here. And beyond that, although this I can be extremely low probability, EI is independent. So that's great. And then you just apply induction. And the induction works because the cardinality of B is strictly less than the cardinality of C.
So in each EJ, so by induction, each EJ given I has probability at most 2P. That's
2P, yes. And this I has size strictly smaller than S, right? Because A is non-empty. Right? So actually I didn't even need to write this. And you didn't even have said this. Let me use this. Okay.
But sorry, is this also something to deal with the fact that in the wrong proof, we didn't consider the fact that the one in Ni can be dependent on the one in I? That's part of the intuition. That's right, okay.
pretty cool.
So you think about it, and then you can do a little better in the denominator. instead of doing the union bound, and that will give you the correct, give the greater constant ease. So maybe this is a good place to stop. We've discussed for about 2 hours. So what we saw today is a basic statement of the local lemma that it interpolates between the counting cell and the independent cell. We showed that the probability can be infinitely small. We saw a general model under which the variable version under which the very large fraction of applications of the local lemma are true. And we saw a proof of the local lemma, right? If possible, I'll maybe do one more example in the next class, and then we'll develop the algorithmic version of the local lemma, right? Or maybe we'll see a few more examples to get more intuition, right? And then we'll see the algorithmic version, which is really very nice. In fact, why don't I tell you what the algorithmic version is? It's due to Moser-Tardos. Let me give you some history behind the algorithmic versions of the local lemma. So sorry, I erase this. So for now, we assume the variable version, but again, like I said, for instance, David Harris's thesis and many others have taken it way beyond the variable version. Right? Okay, but let's talk about the algorithmic version. So originally, people thought that this was really proving the existence of Canadian in the base card. Right? That because the structure you're looking for has inherently very low measure, then there can be no efficient randomized or deterministic algorithms of this form. Right? But slowly people started making progress. The first major progress came from Beck, Joseph Beck, 1990, followed by Malone, 1990. It's some initial progress. Then there's a lot of slow progress by many people, including me. But finally, there was since some of you like information theory, most of them stopped 2009. And then Moser-Tardos, also 2009, made a huge leap on the problem. Right? And their algorithm is in fact a straightforward algorithm. The only important thing is to show that it converges fast. Right? So it's called the resampling algorithm. Or the variable version of the lemma. In fact, we'll see the more general asymmetric version. We have not seen that. The asymmetric version of the lemma, we see that in the next unit. It is simply this. Right? So suppose you have these. Suppose we have the model that we discussed, where you have independent x1 to xn, and d1 to en. Li. So suppose EI depends on some subset of these, right? And these are arbitrary random variables. They can come from any support, just that they are all independent. Right? The algorithm is really natural, beautiful. It's also highly parallelizable. There are some information theoretic insights into it and so on. Why not? Right? You just do the following, right? Initially sample each xj independently from its distribution. Right? So each xj is drawn from some distribution over some subset, right? And these are all independent. So it's a product distribution. Right? And anytime I say sample a variable xj, I always mean independently of all past choices and from the distribution dj. Okay? That's what I mean. Always sampling just means. Right? So now sample all your variables. If you were enormously lucky, and none of these is true, you're done. Right? If not, at least one of these variables is true. Pick one of them arbitrarily. It depends on a set Si of these variables, right? Just resample. That's it. Again, sample every one of them independently from their own distribution teaching.
Every one of them, you mean the neighbors of EI?
Not the neighbors, the variables on which it depends.
Oh, those, yeah.
Neighbor,
Those are the
the
neighbors
bipartite
in the graph, right?
In this bipartite.
In this bipartite graph.
That's it. Okay.
And that works.
Yeah.
Yeah.
The most natural, and Don Knuth also has some interpretation of this, and so on. Knuth has written a nice interpretation of this, using some other.
Would you resample?
That's it.
So like 1 out of P times, you're gonna get a good hit for this particular EI, right? So the real surprising thing is that you're not always damaging the other
Yes,
EIs,
yeah.
right?
In resampling for this, hopefully that will fix this, but then of course, some of the bad event could be triggered and so on. But the amazing thing is, and there is quite a nice information theoretic inclusion in Moser's, and even Terry Tao, even very famous mathematicians like Tao have got interested in this. There is this what is called this entropy compression view. I mean, as you know, entropy cannot be compressed, right? So if there is inherent, the total amount of randomness in a joint distribution cannot be compressed below its entropy. So there are nice entropy compression like arguments. Terry Tao had a proof of Moser's argument, not Moser and Tardos' argument, but this has some nice information theoretic ideas, intuition as well, which I personally don't understand very well. But this is all the Moser-Tardos algorithms, right? Do a zero sampling of all the variables. While there exists some EI that is still true, pick such an EI arbitrarily, just resample the xj's that it depends on. Always independently, always from their given distributions, and that's and show that this converges very fast to an expectation. This is the amazing Moser-Tardos algorithm. And like I said, one of the enormous insights that has come out since the publication of Moser-Tardos is that Moser-Tardos is not just an algorithmic version of the local lemma, that already is a huge contribution, right? But in fact, it's a stochastic process of its own interest, because several of us have shown that from it, you can derive consequences that are true even that are new even in the non-constructive. It will not function.
So you mentioned this entropy compression. I was surprised because I'm recently trying to understand a little bit about high dimensional expanders. I think they use this term there also. Do you know anything about it?
I know nothing about HDLs.
Entropy compression. Okay. Cool. I'm looking forward to it. So are we good? Any questions?
I was just curious.
Yeah.
You have a question?
Is it me? Sorry.
Yeah.
I'm not sure who is being spoken to. Okay.
Yeah, it's you.
So you just mentioned that this process converges, this thing that Moser and Tardos mentioned. Convergence doesn't imply, does it imply that it will terminate?
This algorithm takes is very small. Not any convergence in the limit or any such thing. The expected number of iterations, I mean, this algorithm can potentially run infinitely long or can run for exponential time. But in fact, that the expected number of iterations is a small polynomial amount.
I see. So that's what's converging. So
yeah,
you have convergence of the
not
number
any
of
sort of asymptotic convergence. See.
I see. Oh, that's very nice. And you mentioned this lopsided local lemma at the beginning.
I'm sorry.
You mentioned the lopsided local lemma at the beginning,
Yeah.
where you change the equal. I can't imagine places where that would be used. Can you what kind of a scenario would such a statement be true? That
Great. Okay, can I take 10 more minutes to do?
Yeah.
And by the way, can I know? Okay, can I see who you are and can you tell me who you are?
hi.
Yes. You have to come.
I am Suhail. I'm doing my postdoc with Bruno Loff right now. But right now I'm in India. I was actually there at the Jay Kumar festival where you give a talk. So this is the second talk.
Great. Okay, great. Okay, what does the lopsided local lemma do? Okay, good. For that, we have to introduce a very simple, very natural inequality called the FKG inequality. Okay, the lopsided local lemma says that this is in fact sufficient. Yeah? I'll give you a nice application. Okay, so
But we kind of have a proof, right?
Sorry?
The proof that you just did,
what is
We only actually-
the lopsided? Yeah, we'll also get that. Yeah.
right? We don't use
Because
any.
it's to
Yes,
get less than the equation, basically.
yes, which is what
That's
you
it.
need. Yeah, exactly. Yeah. Mhm.
In fact, let me tell you something more general. Suppose the lopsided local lemma doesn't give you less than or equal to, but it gives you less than or equal to 5 times the probability of VM, for example. Right? Then you'll get 5 here, and you should be able to adjust the other constants so that everything goes through. I've not been able to see a proof, an application that makes use of that, but it's worth keeping at the back of it. Okay, so, okay, lopsided local lemma. Let me first show you an application of the standard local lemma and show that can be pushed further. And this is all hypergraphical continuity. Remember that the hypergraph is just a set system elements. Right? And what you want is, just like satisfiability, so that no SI is monochromatic. Or regular value. Okay. No, so again, suppose right, just like inside, current and release.
So can I guess where you're going with this? Just
Uh-huh.
because that will help me. So you're gonna say something like the probability that this edge is monochromatic can only be less if I know that the neighbors, the other edges of this vertex are not
Exactly.
monochromatic. That's what's gonna amount.
But yeah, yeah.
Okay.
Okay,
Yeah.
color and right? So I mean, it's basically the same as before, except that now you have the factor of 2, because you can go later on group, right? And then, as usual, this is P, and then you just want EPD less than or equal to 1. Right? So you can do the standard local lemma. Where is the lopsided local lemma? Can it help? Instead of m variables like this, write 2m variables. For every HDI, write one separate event that it's all red and a separate event that it's all blue. Okay. So now you have 2m variables. It looks like you've not done much, right? I mean, right? So you now want to avoid all these 2m variables. But the point is, for now, suppose PI says that set SI is all red. Now, if this capital S even contains other edges that SI intersects, right? But if these are all about, okay, so if these are all about that being red, so here you're saying that I'm saying that this particular set is not all red, that particular set is not all red, that particular set is not all red, and so on. And I'm looking at the probability that I am all red, right? I'm set SI, right? If I tell you that, so I'm set SI, I'm concerned that I may be all red. Remember, we have now separated out all red and all blue, right? All red and all blue. Okay. So this event is, let's say that set SI is all red, and suppose this contains some blue stuff, but the blue stuff is sets that I don't intersect at all, but the red stuff can include sets that I intersect with. Then if I'm told that it's not like this set is red or that set is red, this set is not all red, that set is not all red, and so on, it lowers the probability that I'm also red, right? So you can actually show that less than or equal to constant. For that, you need what is called the FKJ inequality. I'll omit that now. Using the FKJ inequality, one can show that, in fact, you can even allow, so now every variant is of the form EI is all red or EI is all blue. When defining the neighbor set, define the neighbors to only be your intersecting sets that are all blue. In other words, positive correlation is okay as far as the local lemma is concerned. Only negative correlation is a problem, right? If I am a set SI and you are a set SI, we intersect, the fact that I am all red and you are all blue are negatively correlated. In fact, they can never happen together, but more generally, they are negatively correlated, right? So the one message of the lopsided local lemma is that it's only negative correlations that you need to count as neighbors. Positive correlations, you can pretend that they are not neighbors. Therefore, we can prove the amount of dependence of the local lemma and get quantitatively slightly better parameter.
So you get a better constant, I guess.
Get a
Yeah,
constant.
I see.
Get a constant. But let me show you this amazing. Okay, here you just improve by a small constant, right? But the first major application of the lopsided local lemma was the following. That is on what is called Latin transversals. Right? The Latin transversal is the following.
So what are you saying? What's
Latin transversals. I'll write it down. So the first major application of the LLLL is what is called Latin transversals. Okay, so here you are given a matrix, but I mean a square matrix, but there's no linear algebra, so you can assume it's an array. Right? So you are given an n by n array. For some algebra C. The alphabet has to be large. It has to be of size proportional to n, but yeah, also the symbols of the matrix, the entries of the matrix. A Latin transversal is a choice of n elements from the matrix, exactly one from each row and exactly one from each column. Right? So they form a permutation. You can take them from the main diagonal or the main, main be anti-diagonal and so on, right? Or any of the n factorial. There are n factorial ways of doing that, right? You want to pick exactly n elements, exactly one from each row, exactly one column, such that no two of the selected elements are the same. That's called a Latin transfer.
For the same letter.
They're the same letter. No two of the chosen elements are the same letter. Right? So Erdős, and there are various conjectures and combinatorics about the existence of these. Erdős and Spencer show that using the lopsided local lemma, they showed that if no element appears more than n over 4 times in the matrix, right? Obviously, for example, if all the matrix attributes are the same or whatever, you can't right, or if if you take two rows and fill them all with the same element, then obviously you can't find any. I mean, if some element appears 2n times, right? You can fill two rows like just entirely that. Obviously, there's no Latin transversal, but they showed that there is this constant 1 over 4e, right? Such that if no element appears more than n over 4e times, then there exists a Latin transversal. So that heavily makes use of the lopsided local lemma. In fact, the random process is the natural random process. Pick a random permutation, sigma, and show that it gives you a Latin transversal with positive probability. Okay. So the random process again is very natural. Of the n factorial permutation sigma, pick one and take the elements corresponding to the permutation and prove that that gives you something that gives you this with positive probability. Right? And let me conclude by saying, so this again heavily uses the lopsided local lemma. Again, you can look up the Alone Spencer book, it describes all this very well. Okay. So I'll just conclude with the following. One of the amazing algorithmic, so Moser-Tardos doesn't cover the lopsided local, right? So later, many people, including my student David Harris and I, we gave an algorithmic version, and Dimitris at Leoptas in his group, but in others also gave something similar algorithmic versions, right? One of the amazing things that came out of this is the following. It's, to me, it is really surprising. So
That you
I
could sample. Or
sorry.
maybe I don't know what you're going to say, but it's really, suppose that there exists, it's not obvious how to find one, right? So, but now I guess Moser-Tardos is going to give you a way of finding.
Does it apply for the lopsided? So yeah, so this was not one of their applications, but later some of us developed algorithmic versions of the of various applications of the lopsided local lemma, including this. But here is something stunning, right? Like I said, originally, even ornamental algorithms, of course, were not at all known for the local lemma or for the lopsided local lemma, right? And for this problem, the input size is n squared here. You have an inline matrix, the input size is n squared, right? And suppose you assume random access to the matrix, which is a reasonable assumption that for any ij, you can pick the ij that way in one step, right? Then we show that our randomized algorithm terminates in O of n expected time, which is sublinear time. Originally, the local lemma was considered like an exponential time the corresponding algorithmic questions were considered exponential time. They became polynomial, and now for some applications, you even have sublinear algorithms. It's to me, it's still stunning. Okay. So take a look at Alone Spencer if you want to get these details. Again, the proof is not very long, just 2 pages. So yeah, this fact is less than a week of the fact is very good use of. So why don't we stop here? We'll resume.
Yeah, thank you, Aravind. Yeah. Okay. Are you good, Suhail? Any questions?
I'm good, thanks.